Good afternoon, everyone. I'm Rohan Gandhi from Purdue University. And today I'm going to talk about PIKACHU. Not the Pikachu in Pokemon, but the system we designed to tackle the heterogeneity in MapReduce. Today, so this was a joint work with Disha and Charlie, who at Purdue from the same lab. So today, there are many web services that are hosted in the cloud. They run on hundreds of thousands of nodes, and every time they face the challenges due to heterogeneity. So with heterogeneity, I mean that there are two nodes. We are trying to do the same work on the two nodes, but they take different amount of time. So heterogeneity is there for different reasons, for a variety of reasons. So one is there have been multiple generations of hardware. So there are nodes that have different CPU, NICs, and disk, among other things in data centers. Secondly, there are nodes that have additional or special hardware like GPUs or SSDs that accelerate processing on those nodes. Even in the world of VMs, even if the VMs are supposed to have the same performance, they don't. Like there have been papers that have showed that the performance on the VMs can vary up to 60%. And these web services, they don't just run on one type of nodes. They have multiple different types of nodes that have different capacity. So with all these factors, there is heterogeneity in the cloud and data centers. And in this work, we designed PIKACHU, which improves MapReduce performance in heterogeneous cluster. So to begin, I'll briefly overview about how Hadoop implements MapReduce. So MapReduce has two phases, map and reduce, and reduce further has three phases, shuffle, sort, and user-defined user-reducer function. So MapReduce runs on multiple nodes. So in this case, let's take a simple example. We have two nodes. Each node runs one map and one reduce task. When a job comes, it starts in the map phase, and the reduce doesn't need to wait until all the map tasks are done. Reduce can fire even when some fraction of map tasks are done. As a result, map and reduce both run concurrently on these nodes. So reduce starts in shuffle phase, where it shuffles the data across nodes, and then the sort executes, where it sorts the data that is output by shuffle. So at one point, it's possible that a node is executing map and shuffle and sort. And when all the data has been received, it's shuffled and sorted, the user reducer runs, and the job is said to be complete when all these phases are finished on all the nodes. So to examine or study the impact of heterogeneity, we divide this whole execution into four different phases. Map only, where a node runs only map tasks. Map shuffle, where a node is running map tasks as well as shuffle. So with shuffle, I also mean sort here, but just for simplicity, I'll use shuffle for both shuffle and sort. So in the next phase is shuffle only, where all the map tasks are over, but not the data is not shuffled yet. So in this phase, all the data has been shuffled. And at the end of this phase, user reducer function runs. So then we go and evaluate the impact of heterogeneity on our local cluster, where we have 2 fast nodes and 5 slow nodes. So we label them fast and slow just because of the CPU they have. And we measure how much execution time is spent in these 4 phases. So in the first phase, it's very short. The map only phase takes only 5% of the time, less than that. The next phase, so that means the reducers start pretty early in the execution. And in the next phase, it's pretty longer. It takes 40% of the whole execution time, but still finishes almost at the same time on both these nodes. But the difference here is that the number of map tasks that are executed on these 2 different types of nodes. So in this case, we observed that almost the fast node, because it's fast, it can process faster, executed 15 times more map tasks than the slow node. This has a consequence on the next phase. So in the shuffle only phase, where it's trying to shuffle the data, the fast node, as it has processed more map tasks, it has more data local. So it can receive less data from other nodes. And in this case, it received almost 7 times less data from other nodes. And as a result, the execution time was significantly smaller than the slow node. And the same observation goes with the user reducer phase. Then we go, so in this case, we ran the word count application which had 680 mappers. So we go change the application, we change the configuration, and we actually see that it's not necessary that the fast node will execute task, will be faster in all the cases. It's really a function of many different factors. It depends on number of slots, what's running in the slots, what is the task, and what are the resources that are available. So it's not always predictable that whether a node will be faster or not, or how fast a node will be. And that's where our contribution comes from. So we say that the job is not going to finish at the same time on all the nodes. There is a big gap here. And we ask like whether we can bridge this gap. If we can bridge this gap, we can reduce the job execution time and save some money. So specifically in this work, we focus on the reducer because for the mappers, because of Hadoop scheduling, they're already load balanced, but the reducer is not. So the problem is how to finish reducer at the same time on all the nodes in the cluster. So to answer this, we first see and why there's this problem, and we see that Hadoop assigns equal amount of data on all the reducers. As their processing speed is different, they take more time on some nodes and they execute faster on others. In PIKACHU, we dynamically adjust the load, where a node gets the data proportional to its processing speed. So we can do the math, and we can say that it's pretty simple, that the ratio of the amount of data going on the fast and slow node is proportional to the processing speed it will get on those nodes. So we denote this ratio of amount of data on fast and slow node as P, which is the partition ratio. And we, in PIKACHU, we calculate this P runtime. We don't really need any information, any prior information for any task or any nodes. We generate all this, gather this information runtime. And as we do this, the challenge is to calculate P is, the challenges is when to calculate P, how to calculate P, and how to use this P to rebalance the data. So that's the design of PIKACHU. So first, we see like what is the accuracy of when we calculate P over time with these 4 phases. So as P is the ratio of processing time in the reducer, it will have a better accuracy when the reducer starts, and it will improve as the reducer goes on. And before reducer, the accuracy will be really bad. So longer we wait, the higher accuracy we'll get to calculate P. But this has a trade-off with reshuffle. So when I say we adjust the data, it's actually we are adjusting the data by adjusting the partitions. So when we assign these partitions when we change a partition from one reducer to another reducer, we may have to move some data which was already shuffled. So this incurs some penalty, and potentially it can outweigh the benefits that we may get by waiting for accurate P. So longer we wait, the higher the penalty is going to be. So we are not the first one to look into this problem. There had been a paper called Tarazu in last year's S+. What they did is they used the map task progress for the reducers. In their case, they don't have a very high accuracy in calculating the P, but they have 0 penalty. So we are a little more brave, and we actually let the reducer run for a while and then calculate the partition ratio P. So this does incur some penalty. So our first contribution is like we should wait until the reducers actually run for a while to calculate P. So the second design challenge was how to calculate this partition ratio. So it's the ratio of progress speeds, progress rate on fast and slow node. We plot this progress rate over time for map and reduce. We see it's different. And then we let the reducer run. We wait for some time and then see what partition ratio is. So Hadoop actually reports the progress rate for every task. And in this case, we observe that the ratio is 2. So we use this progress ratio, we use this partition ratio, and again see how long a job takes in each of these 4 phases. We see that there is still a gap here, and that's not something that we wanted. So Hadoop, the progress score rate reports it. We cannot just use it to calculate the P. So to actually see why this is happening, we we monitor how many tasks are getting finished over time. So in this graph, the blue line shows how many map tasks are done until that point of time. The red and green line denote how many map task output has been shuffled on slow and fast node. So we can see that the red line pretty much keeps pace with the blue line. That means the reducer on the faster node is able to keep pace at the rate the map tasks are being finished. But that's not the case with the slow node. So as a result, we also monitor the CPU usage. So given that the fast node is able to keep pace with the rate at which map tasks are being generated, it doesn't need all the CPU that it can get. And that has an impact on its progress rate that is in the Hadoop. It's always underestimated because it doesn't have work to do all the time. So we account for this CPU usage when we calculate P along with the progress score reported in the Hadoop. So last part of our design is how to reshuffle the data. So in Hadoop, all the reducers get equal amount of data. But in PIKACHU, we use virtual bins, where initially we assign equal data to all the reducers. We wait for some time, and then calculate P, and based on the P, we move a bin from one reducer to another reducer. So in summary, so we address all these three challenges and do everything runtime. So we evaluate PIKACHU. The first thing we do is to see whether the progress is equal on the fast and slow nodes. So here we can see that green and red line both move together, like they are able to progress at the same rate. That's exactly what we wanted. So we then evaluate PIKACHU against Tarazu, which was prior art, and see that we are able to bridge this gap better than what it was in Tarazu. So in the second part of the evaluation, we also see how close we go to the optimal partition ratio. And we are obviously better than Tarazu, and we go pretty close to the optimal partition ratio. We also evaluate in terms of how much penalty we incur by reshuffling the data. And for this application, it turned out it's not significant. It's less than 5%. In the last part of evaluation, we measure the speed up we get over Hadoop and Tarazu. So when we, on our local cluster first, so Tarazu is able to get up to 20% improvement over Hadoop. PIKACHU goes one step ahead, and it is able to get almost 40% improvement over Hadoop. And in this last part, we also evaluate what is the optimal speed up that we can get. So this is like when the job actually finishes at the same time on all the nodes. So we see that there is no big difference between optimal speed up and the speed up we get over PIKACHU. So with PIKACHU, we get almost 92 to 98% of what we would get with in optimal case. And so this was on the local cluster. We also evaluate PIKACHU on a 60-node EC2 in AWS with 40 slow nodes and 20 fast nodes. And even in this case, we evaluate using against Tarazu and Hadoop, and we can get up to 40% speed up compared to Hadoop. So to summarize, so we designed PIKACHU where we adjust the amount of data according to the processing speed on the nodes. So we do this runtime. The measurements are done runtime, and we account for the resources that are used and use virtual bins to adjust the amount of data. Thank you. I don't have an answer for that, sorry.
Hi, I'm Shekhar from Park. I was wondering about your experimental setup, that if you actually switch from, like you had 40
slow nodes, 20 fast nodes, right?
Yeah. If I switch that configuration, would you still get similar kind of speed up? Because what you're doing, I guess, right now is that you're moving reduced computation from slower to faster nodes, because if machines are faster, they will be getting more
Right.
reduced
So even if
partition.
we have a single slow machine, like we can use this PIKACHU even in that case.
Yeah, you can use it, but maybe then those difference would be a little bit smaller because
agree.
already reducer will be running on the faster
Right.
nodes.
Right. We may not get this many benefit. You're right.
Okay, thanks.
I'm in Council, Microsoft Research. So you have a reshuffling penalty because you migrate data after reduce has started.
Right.
So essentially for every piece of data produced by the map stage, you first are transferring it over the network from the map machine to the reducer.
Yes.
And then you have a disk read from the reducer's local storage. Or
Right. So what we do is we let the reducer start as it does in Hadoop. So it will fetch the data from mapper and start processing in a normal way. So after a time, we adjust this piece. So the bin which was supposed to go to reducer 1 now goes to reducer 2.
So you could, what I was about to ask was, instead, if you could do a disk write on the mapper machine initially and do a network read to the right reducer, will the latency be the same for, say, network write followed by a disk read versus a disk write followed by a network read, but then you don't have any reshuffling overhead?
It might actually help, but I'm not sure though, sorry. Thank you. Oh, sorry.
Hi, Michael Condit from NetApp. So you've done a good job of analyzing the case when you have two different types of nodes. You call them one fast and one slow. Does this generalize to an arbitrary number of different types of different speeds of nodes?
So, I mean, in this case, we have just labeled them based on what CPU they have. I mean, we can just call them type 1, type 2, type 3, type n, so on and so forth. So, and then like run the same algorithm for each type.
Okay.
Thank you.